So these limits are same because f is Riemann integrable. This is equal to a to b by previous theorem. Sorry, I was confusing with this Lebesgue integral. Actually, f is Riemann integrable, and the limit of this is the Riemann integral, and limit of this is also Riemann integral. It is done in the previous theorem. So that's equal to 0. So which implies this 0 less or equal to 0 to a to b. It's not okay. I will write a to b g minus h d lambda Lebesgue measure is equal to 0. So which implies that g minus h is equal to 0 almost. It is integrable, and this implies g is equal to h almost everywhere. So g is equal to h almost everywhere. This we have seen. Actually, we need to show that f is Lebesgue. F is not still f is not Lebesgue integral, but we need to first show that f is Lebesgue. F lies between these two Lebesgue integral functions gx and hx. Since f is not measurable here, so we cannot say here f is Lebesgue integrable. Okay. Now we'll see how it's Lebesgue integrable. Okay. So these two are equal. These two are equal. G is equal to h almost everywhere. G is equal to h almost everywhere. Now what we have seen that we have shown that this g is less or equal to g. This g is less or equal to f is less or equal to h. This we have seen. This we have seen that this g is less or equal to f, less or equal to h, but these two are equal almost everywhere, which means that g is equal to f is equal to h almost everywhere. And g and h are integrable, so this means g and h are Lebesgue integrable. This implies or g and h are measurable, therefore f is measurable, lying between two integrable functions. It's integrable. F is integrable. This implies f is Lebesgue integral, not Riemann integral, Lebesgue integral. So this we have seen, this f is Lebesgue integrable. Now we show that its Lebesgue integral is same as its Riemann integral. Its Lebesgue integral is same as its Riemann integral. Okay, let me calculate its Lebesgue integral. Its Lebesgue integral is equal to, by Lebesgue denominator come because limit of phi n increases to f, so its limit n approach to infinity. It's equal to phi n d lambda. It's equal to phi n d lambda. But that we have seen. This is equal to limit n approach to infinity. What's integral phi n? It's a lower sum. It's a lower Riemann sum. Limit of lower Riemann sum. But limit of lower Riemann sum is Riemann integral. So this proves the result. So here f is not only Lebesgue integral, it's an upper function because it has a generating sequence. This phi n is an increasing sequence of step functions such that phi n increases to f, and almost everywhere, in fact, actually phi n increases to g, but g is equal to f almost everywhere. So therefore this phi n, it increases to f almost everywhere, and the limit of the integral of phi n is finite. It is equal to the Riemann integral. So that means this phi n is a generating sequence for f, and hence f is an upper function. So it means that every Riemann integral function is an upper function, and hence the Lebesgue integrable, and its Lebesgue integral is same as its Riemann integral. So this proves the theorem completely. Now we prove the next theorem, which is also very important, which we call Lebesgue's theorem, Lebesgue-Vitali theorem. Okay, Lebesgue-Vitali theorem. Lebesgue. So one thing you note that this Riemann Lebesgue integral function need not be Riemann integral. You can see the characteristic function of rationals, which is equal to 1 for rationals and 0 for irrationals. So therefore that function is actually 0 almost everywhere, and hence Lebesgue integrable because it's constant almost everywhere. But that function is not Riemann integral. This can be seen after proving this theorem actually. Lebesgue-Vitali theorem. A bounded function f, a bounded function function f on the closed interval a b to R is Riemann integrable? If and only if is Riemann integrable if and only if f is continuous almost everywhere. F is, so this is a very important, if and only if f is continuous almost everywhere. This theorem is very important, Lebesgue-Vitali theorem. Okay, this the function f is Lebesgue Riemann integrable if and only if it's continuous almost everywhere. So partitions are previous for each n. For each n, let Pn and let Pn psi and let Pn phi and psi are the functions which we have already defined. Let Pn phi and psi be as they were already be the functions, be the notation, you can say, be the not the function, they are not all functions, be the notations, be the same as in the previous theorem. Be the notation is as in the previous theorem. Okay. As in the previous theorem. So f is Riemann integrable. Therefore, if we assume that this f is Riemann integrable, so then this phi and sin phi increase to f almost everywhere and sin decrease to f almost everywhere. So if f is the Riemann integrable. Conversely, if f is continuous almost everywhere, then phi increase to gx and sin decrease to hx, because in that case we don't have used this Riemann integrability of f. So still we can say this phi is increasing to hx, gx, and sin decreases to hx, while gx and hx are Lebesgue integrable functions. Okay, so these are the functions, these phi and sin, these are step functions as in the previous theorem, Pn with the partition as in this previous theorem. Okay, so assume first that f is, assume first that f is Riemann integrable. Assume first that f is Riemann integrable. So then we have seen in the previous theorem, then phi and it increases to f almost everywhere, and sin it decreases to f almost everywhere. Okay, so let's take let A be a subset of AB such that where this convergence does not hold because it's almost everywhere, such that this phi and x increases to fx and sin x decreases to fx for all x outside of this set A complement. Let this be then this Lebesgue measure of A must be equal to 0 because this convergence is holds almost everywhere. So A is a null set. Now let's define the set D. Let D is equal to A union Pn. Okay, its union Pn and runs from 1 to infinity. So they are the portions. Pn is a portion, so each Pn contains finitely many points, so this union is actually countable. Its union and runs from 1 to infinity Pn. Let me do it. Its union and runs from 1 to infinity Pn. Okay. So this is a countable set, therefore its measure is 0. A has a measure 0, so this implies Lebesgue measure of D is equal to 0. Now we need to show that f is continuous. We show that f is continuous outside of D, so that means f is continuous almost everywhere. We show that f is continuous on this set, this minus d. That is f is continuous almost. That's f is continuous almost everywhere. We show that this f is continuous almost everywhere. So let's choose any point in this. Let x belongs to interval a b minus d. Okay, x is any point outside of this, and epsilon be any positive. Now we have to find delta actually, and epsilon be any positive number. Then obviously there exists some interval. There exists some interval xi minus 1 xi, such that this point belongs to the interval, such that of partition Pn obviously, such that of Pn. Okay, let's fix this of partition Pn, such that x belongs to this. But x is not the partition point, so x must be in the open interval. So that x belongs to xi minus 1 xi. So then you can see this. Then what's phi n s actually? Then phi n s, which is by definition its summation I runs from 1 to 2 power n small mi into characteristic function of xi minus 1 to xi. Since x belongs to the I subinterval, it's equal to small mi. Okay, then this phi n s is equal to msi, and similarly you can see this psi of ns is equal to capital Mi. This follows on similar lines. Okay, so phi n s is equal to small mi, psi n s is equal to capital Mi. So therefore if x belongs to the interval xi minus 1 xi, then we can see this then minus epsilon, which is less than mi minus fx. Okay, fs mi minus fs is a positive, it's equal to 0 in fact, so it's greater than minus epsilon. Raise it here first. It's fs here. Okay, it's fs. It's fs. Mi is same as fs. Okay, and which is less or equal to, but mi is always less or equal to f of x. No, minus f of s, because mi is the infimum on that I subinterval, and that f of x is also less or equal to capital Mi minus f of s. This is equal to 0, it's less than epsilon. Okay, so this holds, so which implies that what's this implies that mod of f of x minus f of s is less than epsilon actually. For all x belongs to this xi minus 1 and xi. So for each epsilon first I can find a neighborhood of the point x such that whenever x belongs to that neighborhood, mod of fx minus fs is less than epsilon. But since xi minus 1 xi is a neighborhood of x, so therefore f is continuous. Therefore f is continuous at that point. F is continuous at the point S. So it's neighborhood of not of neighborhood of S. Sorry, we are talking about f. We are tracking the continuity at the point S. So we need to find the neighborhood of S actually. So for each epsilon there should exist neighborhood, or we can say there should exist delta, because the length of this interval is less than some number obviously. So for each x belongs to that, means whenever mod of x minus s is less than delta, suppose the length of the interval is say delta, okay, then whenever x and s is in that interval, then mod of x minus s will be less than delta. So for each epsilon positive I can find delta such that whenever mod of x minus s is less than delta implies mod of fx minus f of s less than epsilon. So that means f is continuous. In other words, we can say for each epsilon positive we have a neighborhood xi minus 1 xi of s such that whenever x belongs to this neighborhood, the difference of f of x minus f of s, the length of that is less than epsilon. So which means that f is continuous at A. So that proves the one way. Now we prove the reverse. Conversely, assume that. Conversely, assume that this f is continuous. Okay, f is continuous almost everywhere. We show that f is Riemann integrable. Okay, we show that f is Riemann integrable. We show that f is Riemann integrable. So let's choose a point S. Let S not equal to B. B be a point of continuity. Be a point of continuity of f. Be a point of continuity of f. Let's check those points where the function is continuous. We will show that at those points this the sequence file increases to f. Okay, so whenever sequence file increases to f on those points, that means file increases to f almost everywhere, because the rest of the set has measured 0, as f is continuous almost everywhere. Okay, so let me check at these points. So what will happen with the sequence file? So this is the point of continuity. Let epsilon be a positive number. Let epsilon be a positive number. Epsilon be a positive number be given. Then choose delta, because f choose delta positive such that this holds such that mod of f of x minus f of s is less than epsilon whenever mod of x minus s is, this is the point of this is the definition of continuity. But we can expand this as this implies minus epsilon less than fx minus f of s less than epsilon whenever whenever mod of x minus s is less than delta. So this implies f of s minus epsilon less than f of x and less than f of s plus epsilon, adding f of s throughout to this inequality. Okay, adding f of s throughout to this inequality, it will give f of s minus epsilon less than f of x minus f of s plus f of s. So f of s and minus f of s will go, it will remain only here. F of x is less than f of s plus epsilon whenever x minus s is less than delta. Whenever mod of x minus s is less than delta. Now since the length since the limit n approach to infinity mesh of Pn is equal to 0, because you are dividing the lengths of the interval by 2 power n, so as n will approach to 0, the length will obviously approach to 0. This is 0. So pick some k, choose some positive integer k such that mesh of that partition pk is less than delta. We can choose that because it increases to this limit is equal to 0. We can choose k so large such that the mesh of the partition pk is less than delta. So that means every subinterval with respect to the partition Pn, the length of every subinterval with respect to the partition Pn is less than delta. Okay, this is less than delta. The length of every subinterval with respect to the partition Pk is less than delta. So this implies so let this partition Pk is equal to this one. Okay, is equal to say x0, which is equal to a, x1, x2, so on up to xn, which is equal to b. Then this xi minus 1 is less than delta for all I equal to 1, 2 up to n. Okay, this is true. This is true. So let's choose. So let's choose some point. Since s is a point, since we have let s belongs to one of the subinterval, let s belongs to this interval xi minus 1 xi. So on this side it's closed. Okay, so x must belong to some of the interval, so which implies that mod of x minus s is less than delta for all x belongs to this interval, for all x belongs to this, because length of each subinterval is less than delta. Okay, is that clear to you? This because length of each subinterval is less than delta, so whenever we choose point s in this interval, then for any x in this interval, mod of x minus s is less than delta. But whenever mod of x minus s is less than delta, whenever mod x minus s is delta, so this gives from the previous we have this f of s minus epsilon for this particular point x is less than fx. So this implies it's the previous one actually. I want to show this page also here. It's here. Fs minus epsilon is less than fx whenever x minus s is less than delta, but here x minus s is less than delta, so therefore this hold. In fact, this whole inequality will hold. But first I will see this inequality. So let's take the infimum over x. So f of x minus, because x is fixed, is less than infimum of f of x. Where this x lies, it belongs to the closed interval xi minus 1 xi, so that it's less or equal to, which implies that f of s minus epsilon is less or equal to mi. Now look at this. F of s minus epsilon is less or equal to mi. But what's mi? Mi is equal to the value of the function. It's phi k of x, because x is in the ith subinterval. Okay, and this phi kx, it's less than it's less than what? It's less than f of s plus epsilon. Okay, it's less than f of, because mi is less than f of mi is less or equal to f of s, as mi is the infimum of the function f over that interval, and s also belongs to the same interval. But here it's plus epsilon, that's why I have written here strictly less than f of s plus epsilon. So thus f of s minus epsilon less or equal to mi, which is equal to, this is true for this k. Okay, so in fact this inequality holds for each n greater or equal to k. So this case chooses sufficiently large. So in fact this means that so since this phi is increasing, and so it follows that we have chosen k so large such that this mesh is less than delta. So this implies, this gives, so let me see it here, this gives that f of s minus epsilon mod, or you can say this mod of f of k minus f of s. So this is mod of f of k mod of f of k, okay, mod of phi k of s, phi k of s minus phi k of x, it's phi k of x minus f of s. Okay, phi k of mod of so this implies mod of phi k of x minus f of s is less than epsilon. Okay, this is less than epsilon. Mod of sorry, it's mod of phi k of s. Exactly, it's mod of phi k of s here. It's mod of phi k of, let me first erase it here. It is mod of phi k of s actually. Mod of phi k of s minus f of s is less than epsilon. So this is true for each. This implies mod of phi k of s minus f of s is less than epsilon for all n greater or equal to k. So I will write here k instead of n here. Okay, this you can easily verify. This is now n here. Okay, which implies this phi n of s increases to f of s, but s is a point of continuity. So at a point of continuity, phi n increases to f, but the function is continuous almost everywhere. So this convergence is also almost everywhere, because this convergence is true at the point of continuity. So which implies phi n increases to f almost everywhere. Phi n increases to f almost everywhere, and similarly we can see psi n decreases to f almost everywhere. Sign decreases to s almost everywhere. So this shows that our function f is Lebesgue. Our function f is it's a Lebesgue integrable. In fact, here because it's a limit. In fact, it follows from Lebesgue dominated convergence theorem. So this implies f is Lebesgue integrable. F is Lebesgue integrable by Lebesgue dominated convergence theorem. By Lebesgue dominated convergence theorem. Now we calculate this S star. Actually, we need to show that f is Riemann integrable. So this is equal to integral of phi n d lambda, and which increases to integral of f d lambda. So limit of this exists actually, and as upper star fpn, you will see this will decrease to decrease to integral f d lambda. So this limit exists. So thus this implies that both the limits are same. The limit of integral of phi is same as limit of integral of sine. So it implies that this implies that limit of s star pn s s upper star pn s upper star, sorry, it's here s upper star fpn minus s lower star fpn. So this limit is equal to 0, limit this is equal to 0. So that means by Darboux theorem, you can say by Darboux theorem also, or you can apply the previous theorem also. By previous theorem, this f is Riemann integrable. So hence the theorem follows. So that completes the proof of this theorem. In the next theorem, you will see that the collection of Riemann integral functions is a function space, also an algebra that you will do yourself. And one more thing that you will do, which is the fundamental theorem of calculus. That's very simple, that you had done in the BSc course. The fundamental theorem of calculus, which is an assignment. Fundamental theorem of calculus. So you can see this theorem from any standard book, or if you want to see, you can also see it from the book S.C. Malik, or you can also see from this Prints, which is at page number 185. Okay, so this is an assignment for you, this theorem assignment. So that completes this section, the Riemann integral as a Lebesgue integral. Now next we will do the bounded variation functions. Thank you.